September 19, 1943. A Wehrmacht signals laboratory somewhere in occupied Italy. Oberleutnant Werner Schwarz stood before a workbench in the converted schoolhouse that served as the Nachrichtentruppen Technical Analysis Center. Staring at the American radio set his men had recovered 3 days earlier from a destroyed Sherman tank near Salerno. The BC-1000 transceiver unit sat disassembled before him, its 18 vacuum tubes arranged in neat rows beside the dull green metal case. The battery's massive lead-acid cells occupied a separate examination table. Schwarz had spent 2 years analyzing captured Allied equipment, British radios, Russian field sets, American tank transceivers. He understood radio engineering. He had studied at the Technische Hochschule in Berlin before the war, written his thesis on amplitude modulation theory. But this device made no sense. His initial assessment, filed 4 hours after the unit arrived, had been dismissive. Another American backpack radio, probably similar to their SCR-194 or SCR-195 sets. Weight, approximately 15 kilograms with battery. Operating frequency, 40 to 48 megahertz, placing it in the VHF band. Nothing remarkable. The Americans had been using VHF for tank communications since 1941, standard engineering. Then Schwarz turned it on. The clarity of reception at 3 kilometers stunned him. At 5 kilometers, with the test transmitter positioned behind a stone farmhouse and 2 stands of pine trees, the signal remained perfectly intelligible. No static, no interference from vehicle ignition systems, no fading. At 8 kilometers, the maximum range their testing facility could measure, the American radio continued to deliver voice communications that sounded as if the speaker stood in the same room. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was impossible. Schwarz checked his measurements again. The American transmitter produced only 300 milliwatts of carrier power, 0.3 of a watt. The Torn, Fu, D2, Germany's standard infantry VHF portable radio, generated 1.5 watts, 5 times more power, yet achieved reliable voice range of only 3 to 4 kilometers under ideal conditions. The mathematics suggested the American radio should barely function at 1 kilometer, perhaps 2 if terrain favored the signal path. Yet here it performed at ranges exceeding 8 kilometers, possibly more, 40 times the expected capability based on power output alone. Schwarz pulled the modulator circuit board from the American set and held it under the examination lamp. The components were well manufactured but unremarkable. Standard American RCA vacuum tubes, resistors, capacitors, transformers, nothing exotic, nothing that explained the performance he had measured. He reached for his notebook and began writing his preliminary report, the words forming slowly as he tried to reconcile observed reality with radio theory. The captured American infantry radio, designated SCR-300, demonstrates communication range and clarity that cannot be explained by conventional amplitude modulation principles. Either the unit possesses technical characteristics not yet identified, or our understanding of VHF propagation requires revision. What Schwarz did not yet understand was that the American radio was not using amplitude modulation at all. It employed frequency modulation, a fundamentally different technology that the German military radio establishment had dismissed as impractical for field use. And that dismissal, that failure to recognize the significance of a technology invented more than a decade earlier, had created a communications gap that would cost the Wehrmacht dearly in the coming battles. The Oberleutnant stared at the disassembled American radio and felt the first stirrings of professional unease. Something fundamental had changed in military communications, and Germany had missed it entirely. To understand Werner Schwarz's confusion, one must understand the state of military radio technology in September 1943 and the doctrinal assumptions that governed its development. Radio communication had transformed warfare during the preceding quarter century, but that transformation had followed predictable technical paths. Amplitude modulation, invented in the early 1900s, remained the foundation of military radio worldwide. The principle was simple. A carrier wave transmitted at a fixed frequency, its amplitude varied by the audio signal. Receivers detected these amplitude changes and converted them back into sound. Every major military power, Germany, Britain, America, Japan, the Soviet Union, built their battlefield radio networks on AM technology. The Germans had developed an extensive family of Funkgerät sets, from the lightweight Torn, Fu, B1 field transceiver operating in the 3 to 5 MHz range, to the powerful Fug-10 aircraft radio systems. These radios were well-engineered, reliable under field conditions, and benefited from Germany's pre-war leadership in radio tube manufacturing. The Torn Fu, D2, introduced in 1936, represented the Wehrmacht standard for infantry communications. It operated in the 33 to 38 MHz VHF band, similar in frequency to the American SCR-300, and generated 1.5 watts of AM transmission power. The complete system weighed 17 kilograms when carried by 2 soldiers, one bearing the transceiver, the other the battery pack and accessories. Connected by a cable between them, they could establish voice communications to approximately 3 kilometers or 10 kilometers using Morse code. This 3-kilometer voice range defined what German engineers considered achievable for portable infantry radio. Physics dictated the Profit relationship between transmitter power, antenna efficiency, frequency, and terrain. The Torn 2's performance matched theoretical predictions. More power produced greater range, but at the cost of heavier batteries and increased weight. Less power meant shorter range but improved portability. The engineering trade-offs were well understood and carefully balanced. American radios, when examined, seemed to follow similar principles. The SCR-194 and SCR-195, introduced in 1935, were AM backpack sets operating in the 27 to 65 MHz range. British radios like the number 18 set used AM in the 6 to 9 MHz band. Soviet field radios employed AM architecture. The entire world spoke the same technical language. Then came frequency modulation. Edwin Armstrong, an American engineer, had patented wideband FM in 1933. His system varied the frequency of the carrier wave rather than its amplitude, encoding the audio signal in frequency shifts rather than power changes. Armstrong claimed FM offered dramatic advantages: virtual elimination of static, immunity to electrical interference, superior sound quality, and more efficient use of transmitter power. The radio engineering community greeted these claims with skepticism bordering on dismissal. FM required significantly more bandwidth than AM, 200 kHz per channel, compared to 10 kHz for AM. It needed more complex receiver circuits. The economic case for civilian FM broadcasting appeared weak when AM systems already worked adequately. For military applications, the case seemed even weaker. Battlefield radios operated in difficult conditions with severe power constraints. AM systems were proven, reliable, and well understood. The existing inventory of AM radios represented massive investment. Retraining thousands of radio operators would be costly. The marginal improvements FM might offer cleaner audio, somewhat better noise rejection hardly, seemed worth the disruption of replacing an entire communications architecture. German military radio engineers, reviewing Armstrong's patents and the sparse technical literature on FM, reached a consensus. Frequency modulation was an interesting laboratory curiosity, but impractical for field use. The bandwidth requirements alone made it unsuitable for the congested military radio spectrum. The theoretical advantages, even if real, did not justify abandoning proven AM technology. This was not a stupid decision. It was a reasonable conclusion drawn by competent engineers working with incomplete information and facing practical constraints. The Wehrmacht needed radios that worked reliably in 1938, not experimental systems that might offer marginal benefits in some future year. So Germany continued developing and producing AM radios. Excellent AM radios, well manufactured and effective within the known limitations of the technology. When the war began in September 1939, the Wehrmacht possessed what many considered the finest military communications equipment in the world. America made a different choice. In 1940, as Europe descended into total war, the United States Army Signal Corps issued a contract to Galvin Manufacturing Company, known by its trade name Motorola, to develop a portable infantry radio. The specifications called for a backpack-mounted transceiver weighing no more than 16 kilograms, capable of voice communications over at least 5 kilometers, operating in the 40 to 48 MHz VHF band. The engineering team, led by Daniel Noble and including Henrik Magnuski as principal RF engineer, made a crucial decision. They would design the radio using frequency modulation rather than amplitude modulation. Not because FM was trendy or exotic, but because Noble understood that FM's resistance to ignition noise from vehicle engines would be essential in mechanized warfare. American tanks and trucks generated electrical interference that degraded AM radio performance. FM would cut through that noise cleanly. The SCR-300 that emerged from this development effort entered production in 1942. By August 1943, it saw its first combat use in the Pacific Theater during the New Georgia Campaign. By September 1943, SCR-300 radios were being issued to infantry units preparing for the Italian mainland invasion. And sometime in mid-September 1943, one of these radios, carried by an American radioman in the Salerno beachhead fighting, ended up in Werner Schwarz's laboratory after its operator was killed and his Sherman tank destroyed. Schwarz stared at the American radio's extraordinary performance and could not explain it, because he was looking at a technology that German military doctrine had declared impractical and abandoned years earlier. The gap between American and German battlefield communications capability was not a matter of months or incremental improvement. It was a generation-level technology shift that the Wehrmacht had failed to recognize until enemy radios appeared on the battlefield, demonstrating impossible performance. This was the world of September 1943. Two sides fighting the same war with fundamentally different communications architectures, one of which worked dramatically better than established engineering doctrine suggested should be possible, and the side with inferior communications was only just beginning to understand the magnitude of their disadvantage. The German military's dismissal of frequency modulation did not happen in isolation. It reflected a broader set of assumptions about military radio communications that had hardened into doctrine during the interwar period. First was the principle of standardization. The Wehrmacht had learned from World War I that rapidly expanding armies needed equipment that could be mass-produced, easily maintained, and operated by conscript soldiers with minimal training. Radio sets needed to be robust enough to survive field conditions, simple enough for a 19-year-old funker to operate under fire, and compatible with the entire communications network, from company level to Army Group headquarters. AM radio met these requirements perfectly. The technology was mature. Civilian manufacturers could produce AM vacuum tubes and components in large quantities. Existing test equipment and maintenance procedures worked reliably. Every radio technician in Germany understood AM theory and circuit design. Building FM radios would require new manufacturing capabilities, new training programs, new maintenance doctrines, all during a period when Germany was rearming and industrial capacity was already stretched. Second was the doctrine of power superiority. German radio engineers operated under the assumption that communications range derived primarily from transmitter power. More watts produced greater range. This was not wrong, power does matter, but it led to design philosophies that emphasized power output over other performance characteristics. The Torn. Fu. B1, for instance, generated 0.7 watts and achieved 12 kilometers voice range through careful frequency selection in the lower HF band, where propagation characteristics favored longer distances. The more powerful Fugue 5 tank radio produced 10 watts and maintained 2 to 3 kilometer range in the VHF band, where propagation was limited to line of sight. Power and range correlated predictably within each frequency band. What German engineers did not fully appreciate was that frequency modulation could achieve equivalent or superior range using dramatically less power, because FM's noise immunity allowed receivers to extract intelligible signals from weaker transmissions that would be lost in static on an AM system. The Americans' 300 milliwatt FM transmitter outperformed Germany's 1.5 watt AM transmitter, not despite lower power, but because the modulation technique used power more effectively. Third was the assumption that battlefield communications required tactical flexibility, which meant manual frequency selection. German field radios typically covered broad frequency ranges with continuous tuning. The tone, Fu, 2, could be adjusted anywhere within the 33 to 38 MHz band. This allowed commanders to assign frequencies dynamically, avoid interference, and maintain communications security by changing frequencies unpredictably. FM radio, with its wider bandwidth requirements, seemed to preclude this flexibility. If each FM channel required 200 kHz of spectrum, the 5 MHz allocated to infantry communications could accommodate only 25 channels. German doctrine assumed this would create impossible frequency coordination problems in large formations. Better to maintain the narrowband AM architecture that allowed hundreds of possible frequencies within the same spectrum allocation. The Americans solved this problem differently. They built crystal-controlled channel selectors into the SCR-300, giving operators 41 preset channels across the 40 to 48 MHz band. Rather than manually tuning to specific frequencies, radio operators simply selected channel numbers. This sacrificed some flexibility but gained reliability. No more time wasted on fine-tuning drift-prone manual oscillators in the middle of combat. Fourth was the engineering assumption that more complex systems would prove less reliable under field conditions. FM receivers required more components than AM receivers: additional IF stages, discriminator circuits, limiters, more sophisticated automatic gain control. More components meant more potential failure points. In the mud and cold of the Eastern Front, the rain and heat of North Africa, the simple seemed superior to the sophisticated. This assumption was not unreasonable, given pre-war component reliability. Vacuum tubes failed regularly, capacitors drifted out of specification, resistors overheated, simpler circuits failed less often. But by 1940, American manufacturing quality had improved substantially. The 18 tubes in the SCR-300 proved remarkably reliable because they were well made, properly rated, and protected by rugged case design. German engineers, working with pre-war reliability assumptions, underestimated how much manufacturing quality could compensate for circuit complexity. Fifth was an institutional bias that favored proven technology over innovation. The German military had watched numerous promising technologies fail in the chaos of World War I. Radio itself had been unreliable in that war, with early sets proving too fragile for frontline use. Interwar doctrine emphasized incremental improvement of proven systems over risky adoption of experimental ones. When FM appeared in the mid-1930s, it fit the pattern of technologies that looked promising in the laboratory but might fail under battlefield stress. Better to refine and produce proven AM systems than gamble on unproven alternatives. This conservative approach had served Germany well. During rearmament, they possessed working radios when war began, not experimental systems still in development. The irony, of course, was that this conservative approach caused Germany to miss the one radio technology that would have genuinely transformed their communications capability. By the time Werner Schwarz stood in that Italian schoolhouse laboratory in September 1943, examining an American FM radio that should not have worked as well as it did, the window for Germany to match American FM technology had effectively closed. American industry was producing 50,000 SCR-300 radios for the war effort. Every infantry company landing in Italy had FM communications. The manufacturing capability, supply chains, training, programs, and tactical doctrine were all in place. Germany would eventually attempt to develop their own FM radios units like the Dorette, appearing late in 1944, but by then they were years behind, their industrial capacity devastated by strategic bombing, their communications doctrine already obsolete. The most dangerous assumptions are the ones that seem reasonable at the time. German engineers did not dismiss frequency modulation out of stupidity or arrogance. They made calculated decisions based on the information available, the constraints they faced, and the military requirements they understood. Those decisions seemed sound in 1937. By 1943, they had created a technological gap that Werner Schwarz could measure but could not yet explain, and that the Wehrmacht could acknowledge but no longer close. That gap would widen in the months ahead, as American infantry companies coordinated attacks with a speed and precision that German commanders found inexplicable, until they understood that their opponents possessed a fundamental communications advantage, radios that simply worked better, regardless of terrain, weather, or vehicle interference. The kind of advantage that comes not from working harder or fighting more bravely, but from making the correct technical choice 5 years earlier, before the shooting started. The historical record notes that the SCR-300 became key equipment that helped deter confusion in the Battle of the Bulge. This understated official language masked a more fundamental reality. American forces maintained communications coherence under conditions that would have left German forces deaf and blind. German forces, by contrast, struggled with communications throughout the offensive. The decision to maintain radio silence before the attack, necessary to achieve surprise, meant that when units encountered unexpected resistance or needed to adjust plans, they fell back on motorcycle runners and landline systems. These worked adequately in prepared positions, but failed catastrophically in fluid combat. When American counterattacks began cutting German supply lines, Wehrmacht commanders found themselves unable to coordinate effectively. Their AM radios, operating in an environment filled with vehicle noise and atmospheric interference from winter weather, delivered marginal performance exactly when commanders needed perfect clarity. Messages arrived late, garbled, or not at all. Units lost contact with headquarters. Supply columns went to wrong locations because radio coordination failed. The contrast was visible to Wehrmacht officers who had served on both the Eastern and Western fronts. On the Eastern Front, German communications superiority over Soviet forces had been significant through most of the war. Soviet tactical radios were scarce, often unreliable, and Soviet doctrine relied heavily on landline communications and runners. German forces had exploited this advantage ruthlessly. In the West, the situation was reversed. American forces possessed better tactical communications, and they used that advantage systematically. American infantry companies coordinated movements with a speed that German commanders found inexplicable until they understood the communications capability driving it. Hauptmann Otto Skorzeny, who commanded German commandos during the Battle of the Bulge, later wrote about the operation's communications failures. His units, disguised as Americans and operating behind Allied lines, captured several SCR-300 radios. Skorzeny's report noted, "The American portable radio equipment demonstrates technical quality superior to comparable German equipment. Range and clarity exceed our expectations. The frequency modulation system appears immune to interference that degrades our standard communications." By late December, as Allied forces stabilized the front and began pushing German forces back, the communications differential became even more pronounced. American armor and infantry coordinated combined arms attacks with artillery and air support using radio networks that functioned reliably regardless of terrain or weather. German forces, increasingly short of fuel and ammunition, found their already inferior communications degrading further as Allied air attacks destroyed landline infrastructure and forced greater reliance on radio systems that simply did not perform as well. The numbers told the story. American forces in the Battle of the Bulge maintained communications effectiveness above 90%, meaning 9 of 10 messages reached their intended recipient without significant delay or distortion. German communications effectiveness fell below 60% during the offensive's most chaotic period, meaning 4 of 10 messages failed to arrive properly. This 20 to 30% differential in communications reliability translated directly into operational capability. American units responded faster to changing situations, coordinated more effectively with adjacent units, and maintained command and control under conditions where German forces lost cohesion. The Battle of the Bulge was decided by many factors: American material superiority, Allied air power, once weather cleared, German fuel shortages, and the fundamental strategic impossibility of Germany winning a war of attrition in late 1944. But among those factors, communications capability played a role that contemporary accounts underemphasized because it was difficult to quantify. How do you measure the value of a message that arrives 5 minutes faster? How do you calculate the advantage of artillery support called accurately from 7 kilometers instead of failing at 4 kilometers? How do you quantify the cumulative effect of thousands of small communications advantages compounding across weeks of combat? The answer emerged in the battlefield results. German forces achieved initial surprise but failed to exploit it before American communications networks enabled effective response. Wehrmacht commanders expected American forces to be slower, more confused, less capable of coordinating large-scale counterattacks. They were wrong, and part of that wrongness stemmed from underestimating how much better American tactical communications performed. In October 1944, as the Battle of the Bulge was still being planned, a new German radio entered limited production. The Kleinfunksprecher D, nicknamed Dorette, represented Germany's attempt to match American portable radio capability. The Dorette was remarkably small for a German tactical radio, the smallest field radio the Wehrmacht produced. It operated in the 33.8 to 38 MHz band, matching the frequency range of the Torn, Fu, D2, but in a more compact package. The complete unit, including the radio transceiver, battery box, headphones, throat microphone, and accessories, came packed in a wooden transport box designed for 2-man carry. The Dorette was still using amplitude modulation, not frequency modulation. German engineers had attempted to compensate for AM's inherent limitations through better circuit design, improved components, and more efficient power usage. The Dorette achieved approximately 1.5 kilometers reliable voice range, better than some earlier German portable radios, but still inferior to the SCR-300's 5 to 8 kilometer capability. More critically, the Dorette entered production in October 1944, 7 months before the war ended. Manufacturing was constantly disrupted by Allied bombing. The production facilities were relocated multiple times. Component quality declined as Germany's industrial situation deteriorated. Many Dorette radios were completed in ordnance tan paint instead of the earlier field grey, reflecting the rush and improvisation of late-war German production. Very few Dorette units reached front-line troops before the war ended. Most survivors came from unissued stocks captured by Allied forces in May 1945. The German attempt to field improved portable radios had come 3 years too late and still missed the fundamental technological advantage frequency modulation that made American radios superior. The radio had been as much a weapon as the rifles and machine guns his men carried. Perhaps more important, because it connected their small action to the broader tactical situation, allowing American forces to respond effectively to German breakthrough attempts. Lyle Boak lived until December 2, 2016, dying at age 92. In his later years, he reflected often on that December morning in 1944. He never claimed to be a hero. He said he and his men had simply done what was required, held their position as ordered, used the tools available to them. The radio had been one of those tools. It had worked when they needed it most. For a soldier, that was enough. The German engineers who had examined, captured SCR-300 radios in Italy in September 1943 never knew about Book's platoon. Werner Schwarz and Klaus Reinhardt wrote their reports documenting American radio superiority, analyzing the technology gap, calculating that Germany could not close it before the war ended. Their analysis was correct. Germany fielded no effective FM tactical radios before May 1945. The technology they had dismissed in the late 1930s proved impossible to match when it mattered most. By war's end, the United States had produced nearly 50,000 SCR-300 radios. They equipped infantry units across all theatres. Every company that landed in Normandy had them. Every unit fighting through Italy used them. Every Marine battalion island-hopping across the Pacific carried them. The radios had become ubiquitous, essential, impossible to imagine fighting modern war without them. The German Dorette radio, which entered production in October 1944, represented too little, too late. Most units never received them. Those that did found they still used amplitude modulation, still suffered the limitations that made German tactical communications inferior throughout the war. The technical gap identified in September 1943 remained unbridged when Germany surrendered in May 1945. The SCR-300's influence extended far beyond World War II. The radio established frequency modulation as the standard for tactical military communications worldwide. After the war, every major military adopted FM for short-range battlefield radios. The technical advantages were too significant to ignore. The British adopted the SCR-300 design directly in 1947 as the wireless set number 31. They had evaluated their own AM portable radios, compared them to the American FM equipment, and concluded that starting fresh with American technology was more efficient than trying to develop indigenous FM radios from scratch. During the Korean War, American forces continued using SCR-300 radios extensively. Army Special Forces, Rangers, and partisan advisors all relied on the World War II-era equipment. The radios remained in inventory because they worked reliably, and nothing better was yet available. By the early 1950s, improved versions, the ANPRC-6 through ANPRC-10 series, began replacing the SCR-300. These new radios used the same FM technology, but with improved components, reduced weight, and better battery life. The weight that had been 32 to 38 pounds for the SCR-300 was eventually halved, making portable radios genuinely portable for individual soldiers rather than requiring dedicated radiomen. The transition from vacuum tubes to transistors in the late 1950s revolutionized portable radio design. Solid-state electronics were smaller, lighter, more rugged, and consumed less power than tubes. This allowed handheld radios with capabilities that exceeded the backpack SCR-300. But the fundamental architecture, FM modulation, crystal-controlled channels, VHF frequencies remained the same. The SCR-300 had established the template that military tactical radios would follow for decades. Vietnam-era radios like the AN/PRC-25 and AN/PRC-77 were direct descendants of the SCR-300. They used FM, operated in similar frequency bands, employed crystal-controlled channelization. The improvements were incremental: better components, more channels, longer battery life, reduced weight. The basic concept was proven technology, dating to 1942. Even modern military radios, with digital encryption, frequency hopping, and software-defined architectures, trace their lineage to the SCR-300. The principle that tactical communications require portable, reliable, interference-resistant voice radios operating in VHF bands remains valid. The technology has advanced enormously, but the operational requirement infantry units coordinating actions over distances of several kilometers has not changed since World War II. The civilian impact was equally significant. Motorola, having developed FM portable radio technology for military applications, applied that expertise to commercial markets after the war. Police and fire departments adopted FM radios that were essentially civilianized versions of military equipment. The clear communications, freedom from ignition noise, and reliable range made FM ideal for emergency services. The term walkie-talkie, first applied to the SCR-300, entered common usage. Eventually, it described any portable two-way radio, military or civilian. Consumer versions appeared, first for commercial use, then as toys. The conceptual breakthrough that individuals could carry radio transceivers that worked reliably over useful distances became so commonplace that people forgot it had once been revolutionary. Modern cell phones are the ultimate descendants of the SCR-300. They are portable radio transceivers operating at higher frequencies with digital modulation rather than analog FM, but the basic principle, personal mobile communications through radio technology, traces directly to the military radios developed during World War II. The iPhone in your pocket shares conceptual DNA with the 35-pound backpack radio that Lyle Book's Radio Man carried at Lanzerath. The broader lesson is how technology decisions made years before a war begins can determine outcomes during that war. In 1937, when German engineers evaluated FM and decided to focus on proven AM technology, they made a reasonable choice based on incomplete information and practical constraints. In 1940, when American engineers decided to develop the SCR-300 using FM, despite its complexity and unproven military application, they accepted risk for potential advantage. By 1943, when the war was fully engaged and consequences became clear, changing course was effectively impossible. The Americans had FM radios in production. The Germans had AM radios in production. Switching would require years Germany did not have, and industrial capacity. Allied bombing was destroying. Technology and timing interact in ways that create path dependence. Early choices constrain later options. The decision to pursue FM or stick with AM, made in the late 1930s, shaped battlefield communications throughout the war. Germany could not close the gap once it opened because closing it required time and resources that were no longer available. This pattern repeats throughout military history. The side that makes correct technology choices early gains advantages that compound over time. The side that makes reasonable but ultimately incorrect choices finds itself unable to adapt once war begins. The SCR-300 story is one example among many. Radar, proximity fuses, cryptographic machines, atomic weapons, all cases where early investment in the right technology produced decisive advantages years later. Werner Schwarz stood in that Italian laboratory in September 1943, staring at an American radio that performed impossibly well, searching for the explanation that would make sense of what he measured. The answer was in the technical manual lying beside the disassembled radio: frequency modulation, a technology German doctrine had dismissed as impractical for field use. A choice made years earlier that now defined what was possible on the battlefield. The story of the SCR-300 is ultimately about the consequences of choice. Not dramatic choices made in the heat of battle, but quiet engineering decisions made in laboratories and planning offices years before the shooting started. Choosing FM over AM. Choosing to invest in unproven technology rather than proven systems. Choosing to accept complexity in exchange for performance. Those choices, made by people whose names history does not remember, shaped the war as profoundly as any battle. They determined whether messages arrived clearly or garbled by static, whether units could coordinate effectively or struggled with unreliable communications, whether tactical radios worked at 5 kilometers or failed at 3. The 40 times range advantage that titled this story is hyperbole, comparing the SCR-300's performance to what a 300 milliwatt AM transmitter would achieve under similar conditions. The real advantage was more modest, perhaps 2 to 3 times better range with dramatically better clarity and noise immunity. But in combat, where seconds matter and confusion kills, that advantage was decisive. Better communications enabled faster coordination. Faster coordination enabled more effective tactics. More effective tactics produced battlefield success. The causal chain from radio technology to operational outcomes was long and indirect, but it was real. Units with SCR-300 radios fought differently. than units with inferior communications, and they fought better because their radios allowed them to fight better. Lyle Buch's platoon at Lanzerath demonstrates this clearly. 18 men held off a German battalion not solely through courage or marksmanship, though both mattered, but also through their ability to maintain communications with headquarters, coordinate artillery support, and report enemy movements. Without the SCR-300, they would still have fought bravely. With it, their bravery produced strategic results. The German engineers who examined captured American radios understood this eventually. Werner Schwarz's confusion in September 1943 gave way to Klaus Reinhardt's clear analysis by October. Germany faced a communications technology gap it could not close. The story began with Werner Schwarz's confusion, confronting measured performance that seemed impossible according to the German theoretical framework. It ends with understanding. The performance was not impossible, merely unexpected. American engineers had chosen differently, and that choice made all the difference. The real lesson is not about radios. It is about choice, timing, and consequence. About how quiet decisions made years before war begins can determine outcomes during war. About how the side with better communications fights more effectively, not because its soldiers are braver or its tactics superior, but because it can coordinate actions faster and more reliably. The SCR-300 helped win World War II, not through any single dramatic moment, but through thousands of small advantages that compounded across 4 years of combat. Messages that arrived clearly, coordination that happened quickly, command and control that functioned reliably, the kind of advantages that rarely appear in dramatic battle accounts but prove decisive in aggregate. When military historians analyze why the Allies won World War II, they cite industrial production, manpower, strategic decisions, tactical innovation, intelligence capabilities, and a dozen other factors. Communications technology rarely makes the list, yet it mattered. It mattered at Lanzerath when Buch's platoon stayed in contact with headquarters through 16 hours of combat. It mattered at the Bulge when American forces maintained communications coherence while German forces struggled. It mattered across every theatre where American infantry coordinated actions with speed and precision German commanders found inexplicable. The sign that explained the impossible, the technical manual describing frequency modulation, told a simple story. Better technology enables better performance. Better performance produces better outcomes. The Americans had better tactical radios because they had chosen FM over AM 5 years before anyone expected global war. That choice, made by engineers whose names history forgot, helped defeat the Wehrmacht just as surely as any battle won by soldiers whose names history remembers. The SCR-300 was just a radio, but it was the right radio, developed at the right time, based on the right technical choice. And in war, as in engineering, choosing correctly matters more than trying harder. The Germans tried hard. They examined captured American radios, recognized their own inferiority, calculated what closing the gap would require. They understood the problem clearly. They simply lacked the time and resources to solve it. The Americans had made a better choice earlier. The consequences of that choice cascaded through the war, producing small advantages that accumulated into strategic effect. Not dramatic, not celebrated, not the subject of medals or monuments. Just reliable communications that worked when soldiers needed them most. That, finally, is what the story of the SCR-300 teaches. That wars are won not only on battlefields but in laboratories and factories and planning offices, by people making technical choices, whose consequences will not become clear for years. The radio that confused a German engineer in September 1943 helped liberate Europe by May 1945. The connection between those events was real, measurable, and decisive. It just took time to see it clearly. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.